back. Okay, so let's not waste time. Reminder. So hopefully things will go out smoothly from here on, although I have a travel plan in about 2 weeks' time. We'll see how this is, possibly OFIT will deliver a few lectures, we'll see how it works, I'll let you know. Alright, so vectors, tensors, and curved space-time. So we introduced, just to a recap, right? On the last lecture, we introduced the concept of the principle of general covariance. Right? Which essentially stated that if we have an equation that describes the law of physics in a flat space-time, which we know is correct, and if this equation preserves its form, it looks the same in any other frame, then we know it's correct in the general frame. This is called the general covariance. And this is the real reason why we are so enthusiastic about working with vectors and tensors. Because vectors and tensors, to write an equation using vectors and tensors, of course, their derivatives, we know exactly how they transform when we're changing coordinates. So we know that we can easily, or relatively easily, make this equation generally covariant, therefore correct in any space-time, not only a flat space-time. But for that, we needed to understand what do we mean by vectors in chord spaces, right? And we spent the whole last lecture with some more abstract mathematical structures, just to make a very simple claim that we can identify vectors can be identified with directional derivatives. And when we say directional derivative, this is really a generalization of the idea of partial derivatives. So we had a manifold, we call M. I did not bother to fully explain to you what is a manifold. I just made a general statement that a manifold M is a space which is locally flat at around each of its points, but globally it does not have to be flat, or it's not even flat, right? So this is a good manifold. Bagel is a good manifold, right? But we don't have a porcupine. This is not a good manifold. Also, the manifold doesn't have any edges, right? So in math lingo, we'd say, right, there's an open set and closed set. So a manifold is really an infinite connection of infinite number of open sets. Yes.
Does the derivative have to be continuous as well? Like, can it have?
Yes, it does have to be continuous. It's a question of how much continuous. It's really C infinity, right? But,
it has to be C infinity.
No, it doesn't have to be C infinity. It has to be continuous up to a level. For this course, we don't need more than C1. C1 means it only exists to one first derivative. But we don't really need that, right? So we don't need to get into it. But for example, right, this is a manifold, but this is not a manifold, right? This is not. So there is a reason why I didn't do that, because I think it's not, it is there in my lecture notes. So if you're really interested, you can simply go and read it. And we can have a tutorial. I didn't do it because of lack of shortage of time, because it's a shorter semester, and I think that it's more for the mathematical completeness than for the real physical need of what we're doing. So going back to our point, right, we had a manifold M, and the thing we can do around this manifold, we have a point P. Right. Since this is locally Euclidean, we can always put a set of coordinates at P. But what we can do in general about the manifold is to specify a curve that goes through P. Call it gamma, and this curve is specified by some parameter lambda. Right? So lambda equal to 1, lambda equal to 2, lambda equal to 3. And again, the simplest way of think of it, I am going to hike on the Israeli trail. Right? So you know what curve I'm taking, and it's enough that I give you one number that you know exactly where I am on the trail. Right? I've just reached point number 3, then you know point number 3. So really, the correct way of thinking of that really is that it's a mapping between numbers and manifold. I give the number, you know where I am on the manifold. But we really don't need to get that deep. And then at the point P, I can specify a vector to be the tangent vector. Essentially, it will be the tangent vector to a curve. So it will be the lambda. And if I want to put coordinates, which I can always do, right? And I can put a set of coordinates in the vicinity of P, which I'm allowed to do because locally this is Euclidean. So this will be coordinate 1. D over dx1, which is equal to d1, and this will be d over dx2, which is d2. So the vector that is defined by d over d lambda is, I can simply write this dx mu over d lambda d mu. And of course, there's an infinite number of curves that go through this point P. This is just one basis that I selected. Of course, I can select any other basis. So this is known as the coordinate basis. Right, what I just plotted. This is known as the coordinate basis. It's a basis that is associated with a certain set of coordinates that I chose.
So is it possible to do this also in 3-dimensional local coordinates?
Of course.
Yeah.
It's n-dimensional. I only draw it in 2-dimensional.
Okay. Just verifying.
The whole point is that you do it in any dimension that you want, of course. Space-time is 4-dimensional, but I cannot draw it in 4-dimensional without confusing you. I can only do 1-dimensional, which is sort of trivial, and 2-dimensional, which is easy to visualize. But obviously this can and is generalized to n dimensions. Right? It's simply much easier to visualize it in 2 dimensions. So that's what we can do. Okay, so this is a coordinate basis, of course, for TP. TP is the tangent space to the manifold M at P. Right? And once we have that, right, if you want to change to different set of coordinates, so the red coordinates, let's see what kind of use. Let's do that. Purple coordinates, right? I can do like that one. I can change from d mu to d mu prime, d2 prime, d1 prime. And of course, I can simply shift the entire grid to set the new coordinates. Hope it's not getting too messy. Then obviously d mu prime is just dx mu. Dx mu prime. And the transformation law of the vector components. It's exactly what we did for the flat space, right? You can just write any vector v. It's v mu d mu. This is the component in the basis mu. Right? That's a great way to think of that. And of course, the vector itself is not changed when we're changing coordinates, right? This is the blue is my vector. This is my vector. Right? I have the red or green coordinates, and I have the black coordinates. The vector itself doesn't care which coordinates I'm using. Right? It's just the way I describe its components. So of course this is equal to v mu prime, v mu prime. Which from here, v mu prime, dx mu over dx mu prime, v mu prime, from which we get v mu prime is dx mu prime over dx mu, v mu, which is a transformation law of the vector components. There is really nothing else you can do. All this notation makes perfect sense now that you look at it. Why am I insisting on putting upper indices versus lower indices? Yes?
You say it's v mu dom mu, not like dom mu v mu. That means
this is the component of the vector in the direction x mu.
yeah, but
Remember, there is a sum over mu here.
yeah, of course, but because d mu is on the right, and it's like a covector, right? It's like a thing that acts on a vector. Shouldn't it be like d mu v mu?
No. This is a number. This is a vector.
Okay. So okay.
This is just a number.
Okay, but it is like an operator that you put on the right of it, covector, and then you get the scalar. Okay. No.
We said vectors can be identified with covariant derivatives.
Yes. Okay. Yes.
D over d lambda. This is the vector, which you can write as d lambda.
Okay. Okay, that's fine.
Maybe what confuses you is because the x mu is in the denominator. Okay. That is, of course, the transformation law of the contravariant vector. Of course, it's much easier for us, it's often easier for us to simply use the components to describe the vector. We often don't even think of that, but that's what we really do. Actually, you're going to see that we're going to clean up many things that you've been doing sort of automatically without even thinking now. Maybe, not inside of your head, so I don't know what you're thinking of. But we'll say that clear up these things. All right, so these are vectors. Said life is not made only of vectors. Okay, any questions before we move on?
Yes.
Further questions? Yes.
So when I'm talking about a vector d lambda, so like it means nothing if I'm not specified first gamma, like the.
No, it's there by itself. I just said that when we are talking about vectors on a curved space, okay, the problem was how to define a vector to a curved space in a way that is completely intrinsic to the space. I cannot leave the space. I'm limited to the space. and I, the only thing that I can do that is intrinsic to the space is to put curves along the space. This is something which I'm allowed. Right? Again, think of it in terms of, you're in a ship. You can circulate Earth, but you can't go inside and you cannot go outside. You cannot go to space. You cannot, so you're limited, right? But you can do various routes, right? On Earth, you can sail from here to New York, from here to.
So once
So you can set the path through Earth.
once we define d lambda as the d mu, so we can forget about gamma.
First, yes. I mean, gamma is just. We said that the most natural way to define a vector is a tangent vector to a curve.
Yeah.
And there are infinite number. First, the vector is defined at the point P. Right. That's the first thing. Don't forget that. So we have a tangent vector to the curve at the point P. And the way we define it is general. So we have some curve, and it will be a tangent vector. Essentially, every vector will be a tangent to some curve. Right? D mu, these are the coordinates. We don't need that. We don't need. I can have a vector without the coordinates. It's easy for me to define a vector via its components at a given coordinate system. If I specify, I have a point here. Or I have an object here in space, right? I put an object here. Ball. Where is this ball? It's there, right? If I want to describe to you where is the ball, then I better put coordinates, and I can tell you, okay, this is x, this is y, and the ball is x0, y0. Right? To tell you where the ball is, it's easier for me to use coordinate system. But the ball is still there even if I don't have coordinate system. So the ball, it's a particle, it's something. It's still there. Coordinates are for me. Right? This is the thing. Use different coordinates. Yeah, use different coordinates. X prime, y prime. The same object will be described in different coordinates. The same place. Nothing happened to the object. It's just the way I describe it. The same thing exactly happens here. Only this is generalized to curve space. Okay. I'm now no longer limited to Euclidean flat spaces, because this is a general definition which is true for every curved space that I may have. And again, the simplest way for me, okay, I may have different. To think of it is think of an object on the surface of a sphere, like the surface of the Earth, like a ship that is traveling and is somewhere in the ocean from here to whatever. What's here? Okay. What about covariant? So, further questions? No? Well, that means everything is clear. I mean, if I ask you about that in the exam, no problem, everybody. So, what about covariant vectors? So essentially, again, we're basically repeating the same thing we did for the flat space. We said covariant vector omega is a covariant vector omega. Right? It's a linear map from TP to R. Omega belongs to the cotangent space, TP star. Right? And we gave an example of the one form. It's called one forms. Again, I won't get into P forms theory, simply because we won't have time. It's really, really nice. That's the way that will help you. If we get into that ever, then you'll understand why determinants have these plus and minuses. If you will ever ask yourself. So omega belongs to the TP prime, and we said we gave an example. What is the example of a one form? The gradient, right? This is a classical example. If you have a function f, which is defined everywhere, the gradient, df, is a one form. covector. It's called the F. And the way the covector acts on a vector, right? So df it operates on a vector which will be d over d lambda. It's exactly what you write. Df over d lambda. F is some function on a manifold F. Just you see that I put on a small comment, right? The covector is df, it's not f itself. I cannot think of the function f as a covector. The reason is, if I want to take the derivative, I need to know what is f at different points, nearby points to the point p. And I can't do it at this stage. I need to have things that are only defined at p. And the gradient is defined at p, so it does what we want. Okay?
Can you repeat it?
Yes. You could naively say, okay, why don't I think of that as a vector, and of that as a covector. Right? Why did I get df operating with d over d lambda? So why is the gradient the covector and not the function itself? And the reason is that if I want to do that, I need to know the values of the function at different points nearby p. P itself will not be enough. Just one value of the function. Right? So that's why I need to know the gradient of the function. Okay? Again, I'm enforcing, that everything I do is limited to the point p. So again, very similar, like we had the partial derivatives d mu along the coordinates that we defined gave us a natural basis for the vectors. Then they have the same thing. The gradients of the coordinates, the gradients of coordinates. Again, coordinate is something which we put by hand. Right? It's my choice of coordinate functions. Coordinate functions. X mu provide natural basis for the cotangent space. So it's exactly the same game to play. So in flat spaces, remember we had theta u prime. These were the basis, right? Operating on a basis vector mu. And this was a delta mu. And this was from flat space. Of course, now what we're going to have is exactly the same thing. dx mu that operating on d mu is dx mu over dx mu equals delta mu. Again, don't get confused by the symbols. What this just says again that I have a manifold. I select a point. Around that point, I define basis vectors. I can just take the gradient along these basis vectors. That's all. Yes.
So the reason why the basis is differential is because it's curved space, not Euclidean?
No, nothing to do with that. This is just because I generalize it. The way this is defined is true, of course, in flat space, but also in non-flat space.
But I thought that they have to be, the basis vectors have to be static.
They are static. They are defined only at the point P.
Okay.
If I go to a different point, I cannot use the same basis vectors. They don't belong there. Remember, vectors belong to a point. Okay? It's only at P. The really correct way of drawing it, right? I'm putting a tangent space TP, and everything is now on that space. So of course, gradients of the Warren functions were a natural basis for cotangent space, and being a basis, every object omega that belongs to TP star I can write as omega mu dx. Just decompose it into the components in that specific basis. And of course, the transformation properties of omega is pretty straightforward, derived from the same transformation law of the coordinates, right? So we just have, I mean, really that's the nice thing about these things. Once you accept that, there is nothing you can do. You're just forced to go through that, right? So transformation law of the basis vector, transformation law of covector, right? Dx mu prime is dx mu prime, or dx mu, then for the components, omega mu prime will just be dx mu over dx mu prime omega mu. Which again makes perfect sense. What else can you do, right? If you're accepting these notations. So of course the opposite way as the transformation law of the vectors. So this is a transformation law of a covariant vector. What about tensors?
Transformation of a tensor.
What?
You need something like applied to the metric tensor or something.
What about general tensors?
It's just a what do you call a product of.
It's an outer product, right? So every tensor T, right, which has K upper indices and L lower indexes, right? Right, it's T mu 1 mu K mu 1 mu L times the basis, right? So we have V mu 1. I'm going to write it as an outer product. This is called an outer product. Have you seen outer products before? What? Likely yes. It's not something that okay. And outer product is dx mu1 L. This is outer product, also known as a tensor product, which you can simply think of as operating on different spaces, and then just adding those together. Of course, the order matters. Okay. So when we're doing coordinate transformation, it's pretty straightforward. So coordinate transformation. T mu 1 prime mu K prime mu 1 prime mu L prime. How do I transform the components of a tensor?
Transform each one out of the outer product.
There's really nothing you can do. So So it's just dx mu1 prime over dx mu1, dx mu2 prime over dx mu2. Right? Dx mu k prime over dx mu k. And then the lower indices are, of course, exactly the opposite. Dx mu1 over dx mu1 prime times dx mu l over dx mu l prime times t mu1 k mu1.
Wait, shouldn't the new be in subscript?
Which one?
The news. Yeah.
Yeah, they are.
They're in subscript?
They are subscript. Obviously.
Okay.
I am taking the derivative, right? This is the old, this is the old coordinate, the original coordinates.
Oh,
right?
oh, it's the prime.
It's
Okay.
the coordinates, right? So I'm changing from coordinates from the mu to mu prime.
Okay.
Or
Yeah,
mu
yeah.
O prime, right? Mu to nu prime.
So the position of basically the prime, how you're differentiating the prime determines whether it's superscript or subscript.
Yeah.
Oh, okay.
It's very simple. Really, it's like, it looks confusing, but it's really simple at the end. So I know I put an example. I realize this is the point that people get confused a little bit. But I say there is nothing really to be confused of, because this is, in fact, what I'm writing are things that you use. You know that, and you don't even know that you know that. Maybe, right? So, example, right? So I consider a symmetric example. Symmetric is always a 2n. Right. 0, 2 tensor, which I simply write as x1 is x, x2 is y, and s mu nu. I just write it as x0, 0, 1. Right. So this is really s, is the tensor is s mu nu, right? Dx mu, dx mu. What we really have here is x times dx squared plus 1 times dy squared. Right?
When you say 0, 2, it's like 0 vectors, 2 covectors. It's in that order.
Always this.
Oh, no, it's good enough.
0, 2.
Okay.
It's the rank of the tensor.
Oh, I just didn't know if it was vectors, covectors, or covectors, vectors.
I don't know. When we spoke about tensors, I defined exactly what is its rank KL tensor.
Okay.
Right? Again, it's a linear mapping from K covectors and L vectors. So if we do a coordinate system, so change coordinates. If I want to change coordinates, right? So here I just select x prime is x to the power 1/3, and y prime, what did I select? E to the power x plus y, just because I want to. And when I do that, that means that I can write down x is x prime cube, right? Y, I need to take the log, so it's log prime plus x, which is x prime cube, sorry, minus x prime cube, and then you take dx in 3x prime squared dx prime, and dy is 1 over y prime dy prime minus 3x prime squared dx prime. Which is exactly what you write down if you want to change the coordinates. And I can write down s in these new coordinates, like x times dx squared plus y plus dy squared. So this is just dx squared, it's just a 9 times x prime power 4. Then I have here dx squared, and from here I have done for times x prime. X right to the 4 times 1 plus x prime cubed times dx prime squared. I have to square that. I just have to remember that dx prime dy prime is not necessarily commutative with dy prime dx prime, so I just have to be careful how I write it. So it's a minus 3 x prime squared over y prime dx prime dy prime plus dy prime dx prime plus whatever is left from here plus 1 over y prime squared squared. If I'm going to write that in the matrix notation, I'm going to write down as mu prime to be x prime to the 4 plus x prime cubed. I have a minus 3 x prime squared over y prime minus 3 x prime squared over y prime near 1 over y prime squared. That's all. It's exactly what you would have done if I ask you to change coordinates. You do it anytime you're changing coordinates. So it's actually quite, at the end of the day, it's quite straightforward. All right, questions? Is it clear what is written here? Some of you are not saying anything, just looking, staring at me. Some of you are nodding in your heads, but I'm not sure what it means.
I need to do it to find out.
You need to do it. Okay, then we'll make sure you give you homework so that you do it so you can find it out. Yes, guys, I mean, you know, by now, you see what I mean, that it's not enough to sit down in the classes. Listen to this. Actually, you have to do it by yourself. Otherwise, it's not going to work. Okay. Now let's see what it means. I'm going to show you another things, other few things that you are familiar with, but you never knew that you're familiar with. So let's talk now about few extra things which we need. They're actually quite crucial for the time being. Volume elements, curved spacetimes. Volume elements in curved spacetime. And tensor densities. First thing, which is quite important, so let's just do it. What about the metric tensor? Metric tensor is obviously a tensor. Metric tensor. Remember, we define it as eta alpha beta d psi alpha over dx mu d psi beta over dx nu. If you want to make transformation, mu prime, eta alpha beta d psi alpha over dx mu prime d psi beta over dx nu prime, eta alpha beta d psi alpha over dx mu, right? Dx mu over dx mu prime, right? I just express it now in terms of the old coordinates. D psi beta over dx nu, dx nu over dx nu prime. This is of course G. as dx mu over dx mu prime, dx mu over dx mu prime, g mu. Now, obviously, this is the tensor. So this is a covariant tensor, right? See the transformation law of the coordinates, right? So this is the new coordinates, g expressed in the new coordinates. How do I relate it to g expressed in the old coordinates? And this is just take the derivative of the coordinates. Obviously, this is a covariant tensor.
Is it delta?
What?
Yeah.
Why do you say that?
In the parentheses.
This will be delta mu, right? But this depends on which coordinates you use. Only if I'm using Cartesian coordinates.
Isn't there a delta for the
There is a chronicle delta, right? There is a delta mu nu. This is the chronicle delta. That is a mixed tensor. This is a mixed tensor. 1, 1 tensor. What about the affine connection?
mixed tensor? It's a 1-2 tensor. No, it's not.
This is not a tensor.
Why so?
It's not a tensor.
Because it doesn't transform like a tensor.
Asana. Well, then transforming. I mean, hopefully we'll have time to transform it today. This is not a tensor. It's not transformed like a tensor. And that's why I allow myself. That's the only reason why I allow myself to write it. You know, it's lower indexes below the macro. It's not a tensor. Another important quantity, which is a non-tensorial quantity, is the determinant of G. So G, I call it simply G. This is the determinant of G. It's defined as a minus determinant of G. There is a minus sign here. Absolute value. That's not a tensor. If I take the transformation law of the metric tensor, and I take the determinant, you maybe remember that from your linear algebra course. What happens when I take the determinant of that? What do I get?
It's epsilon ijk.
G x mu prime. So this is G expressed in the new coordinate system. Is dx mu prime over dx mu minus 2 G of x mu. Or G prime is dx prime over dx minus 2 G. What is this dx prime over dx?
Delta.
Yeah.
Delta ij. Delta.
No. This is the Jacobian,
Ah, right, yeah.
right? Agree? You know what is Jacobian from your linear algebra courses, right?
We even had it here,
We even had it here.
the transform of
This is the Jacobian. So the determinant transforms like a scalar, but we have this extra factor of the Jacobian. We're changing coordinates. Okay? If not, if you're not sure, then go to your linear algebra where you learn about determinant and see that it's the right answer. Now this number that we have here, this number, minus 2, this has a name, it's called a weight. G, because it's doesn't transform like a vector, it's extra Jacobian. This is called a tensor density. This is really a scalar density, because this is scalar. It's a scalar density, which is of course a special case of a tensor density. And we say of weight minus 2. That's a technical name for it.
This is not the power.
This is the power. Power is called the weight.
Why is it called weight? What does it mean? Why does it call weight?
Wait, 5 minutes. Let me see. She's telling you that you know it. You just don't know that you know. Why do we care? If we look at the volume element under general coordinate transformation, everything we're doing right now is just coordinate transformation. What is a volume element? Volume element dn x prime, and I want to connect it to dnx. So I'll throw from x to x prime, right, the volume element. And what do we get? Jacobian. That you remember. This is dx mu prime over dx mu. The volume element picks up Jacobian. If I want to get an invariant volume element, what do I do?
Do what?
If I want something which is invariant, what do I do? Come on.
Oh, multiply with G?
Right. Multiply not with G, but with square root of G. Right? Because G is so to get so square root of G times Vnx is an invariant volume element. Oh, I tell you that you know that. For example, I have a example. A Euclidean space, three-dimensional, which I write in Cartesian coordinates. And how do I write the 3D space in Cartesian coordinates?
Dx squared is
The r squared plus
r squared d theta squared
r squared d theta squared plus
sine squared
sine squared
theta.
theta d phi squared.
SF. Maybe like the example of a polar would be easier.
What example?
Of like 2D and polar coordinates would be easier.
Okay, that's a 2D if you want. I'm giving you now an example of 3D. Yeah. So if I want to write, what is the metric G mu nu?
It's diagonal, right?
Of course it's diagonal. You can say it's
Yeah,
diagonal.
no,
You only have parts on the dr squared, d theta squared, d phi squared.
Yeah, no, I'm saying it's 1 r squared.
So 1 here r squared,
R squared sine squared.
here r squared sine squared theta. Just a second. So what is G? The determinant of this matrix?
R to the 4 sine squared theta.
R to the 4 sine squared theta. What is an invariant volume element?
It would be r r square sine theta dr.
Right. Take the square root. So this is r square sine theta, and then dr d theta. You fine? Okay. Told you know that. Now you know why you know. Okay, now questions. Yes.
If this is the n dimension נפח ממדי.
What do you?
What? So why this is not the nth root of g? Why the weight is always 2?
Because when you take the determinant, that's what you're going to get. You're going to get the Jacobian to the power minus 2. To calculate the Jacobian, you have to solve the full matrix of n by n. Right? If you have a 2-dimensional, it will be a 2 by 2 matrix. If you have a 3-dimensional, it's a 3 by 3. But it's still the same Jacobian. Jacobian is a number. Right? It's the determinant of the Jacobian matrix. Okay, so go and say, it's a good point to go back to your linear algebra course and refresh you. Think about memory about Jacobians if you need to. But yeah, it's nothing to do with the dimension. It's always minus 2. That's right. Right. More questions? No? Okay, just one point about notation, which is just a notation that you know. So metric is called in canonical form. Metric is in canonical. If I can write this G mu nu as a diagonal of first minus ones and the plus ones, and then a 0. Now, of course, if you have zeros here, that means eigenvalues would be 0. That means the metric is degenerated, which we cannot find the inverse metric. Fortunately, you don't care about it in this course. Actually, not in any other course that I know of. Maybe in some mathematical theories you do care. I'm not a mathematician, so I don't care. If all the signs are positive, if all signs are positive, then the metric is called Euclidean or Riemannian. If we have a single minus, if there is a single minus, then it's called a pseudo-Riemannian. Another name is Lorenzi. What metric do we have in this course? What type of metric? Lorenzi. Only all the metrics we're going to deal with are going to be Lorenzi. Right? I think it's quite cool. Right? Working very hard and essentially it's this actually we know. More questions before we go on? You guys at the back, not saying anything. I don't like your smile. Kind of smile that I'm not sure what it's. All right. Okay, so the next thing we need so that we can move on about tensor densities. Levi-Civita. We said it's tensor. It's not really tensor. It's cheating. It's a tensor density. So it's a Levi-Civita tensor density. So in flat space, we have epsilon, which I'm now going to put in as a tilde. This is a flat space. Right? There's some tilde of mu1, mu(n) is defined as +1 if mu1 to mu(n) are even permutations of 0 to n minus 1. Right? It's a -1 if this is odd permutations of that, and a 0 otherwise. And we said this is a tensor, but this was a lie. I was cheating. This is really not a tensor. This is called a Levi-Civita symbol. Levi-Civita symbol. And this is how we're going to treat it from now on.
Yeah, I remember learning about this, but what I don't remember is how do we determine odd and even?
What is the question?
How do we determine odd and even? What is it?
Odd and even permutations of 0 to n minus 1.
Okay.
0, 1, 2, 3. This is even. Everything, with one switch, it becomes odd. 0, 1, 3, 2, this is odd. 0, 3, 1, 2, this is even. How many permutations I need to? Here I have 0 permutations, so this is even number. Okay? Slightly confusing, not too much. 0 permutation. 1 permutation. What about 1, 0, 3, 2? How many permutations have here? What?
2?
2 here, right? 1 here, 1 here. So this is even permutations. About 3, 1, 0, 2.
3?
1, 2, 3. So after 3 permutations, I got 1, 0, 2, 3, and then I have another one here, so I need to have 0, 2, 3. 1, 2, 3, and then a permutation. This is even. All right, play with that. So anything that is defined like that, so it just gets plus, minus, +1, -1, or 0, based on the number of permutations relative to 0 to n minus 1, is called a Levi-Civita symbol. Doesn't matter what are the coordinates. Right? It's doing any coordinate system. Tensor, because when we are, this actually, I read it and say, okay, this can be found in any mathematical textbook. I don't know if you can find any mathematical textbook, but you can actually find it. So it's okay. So if you're switching the coordinates, when changing coordinates under coordinate transformation, this becomes epsilon tilde of mu 1 prime mu n prime. You have this extra Jacobian x mu prime over dx mu epsilon tilde mu 1 mu n dx mu 1 over dx mu 1 prime x mu 2 over dx mu 2 prime dx mu n over dx mu n prime. So yeah, when I honestly, when I first played with that as a student, I remember that it was okay. You know that. Okay, I don't know that. So I don't know if people teach us that today in linear algebra courses. Yes or no? Today?
We had a really short.
Yeah, but of course not, right? It's true, right? So I can, if you really want, I can point you to some textbooks where you can find it. But ask ChatGPT will tell you. Yeah, but you can easily prove that. It's not that difficult. But yeah, honestly, I don't think I remember that in my linear algebra course. So I don't expect you to learn that, but it is true. So really, this is a tensor density of weight 1. This is a tensor density of weight 1. But this tells us exactly what we need to do to make it a tensor. What do you need to make it a real tensor, not a tensor density?
Need to multiply it by.
Multiply by some tensor density of weight minus 1, which is square root of g, of course, right? So a real tensor. So we define the Levi-Civita tensor is defined as epsilon mu1 mu n is square root of g, the determinant of g, times Levi-Civita c. So this is the true definition of the Levi-Civita tensor. And sometimes we prefer to use the Levi-Civita with the upper indices, in which case we have epsilon mu1 mu n. Then we have to put the sine of g, and here times 1 over square root of g epsilon. Yeah, see, I put another note here. In some basic sense, it doesn't really matter to us here, but just that you know, in case just for fun. In some sense, it's not a real tensor because it cannot be globally defined on any manifold. And the classical example is the Möbius strip that you see. You cannot really define it on the Möbius strip properly globally. Of course, you can define it locally. So in some mathematical way, it's not a true tensor. Yeah, I even point out there is a textbook by Schutz, but it's not the same textbook that I point out here. Geometrical methods for mathematical physics. Actually, it's not that great. But because there are some things there that it doesn't do properly, but some things it does. So you can have a discussion there if you have extra time. Okay, questions? Yes.
When you say not a true tensor, do you mean a pseudo tensor or just
No, it's a tensor, but it cannot be globally defined on every space. Since we don't really care about Möbius strip, except that we know that it exists, because we are doing here physics, doing GR, we're not doing a math. Just that you know, if you want ever want to study that in a high math level, that don't say, oh, Asaf said this is a tensor. Somebody will tell you, no, it is a tensor. Yeah, locally it's fine, but globally it's not exactly a tensor. Okay, that's it. We're not going to make any use of that, so that's why I'm not writing it. Just for your general knowledge. All right. Any further questions?
So what is the significance of tensor weights?
Just gave you 2 examples.
Oh, okay.
Invariant volume element.
Yeah.
And you can use them to. Not everything is a tensor. Some things in life are not tensors. Again, in this course, what I just said is enough for us in this course.
Mm-hmm.
We're not going to go through more advanced theory here. Let's stick with the basics. I think basics here is advanced enough. Okay. If you ever want to study theories of higher dimensional, do that. Not right.
So you always need a zero weight to be so it can be invariant.
Well, what I have proven to you is that an invariant volume element would be square root of g times the dnx, rather than dnx, and I showed you actually know that. You just didn't call it like that. If you're using in a non-Cartesian coordinate, if you're using Cartesian coordinates, right, invariant volume elements, dx1 times dx2 times dx3. If you're using others, then you have this extra thing here, but now you know how to calculate it in every coordinate that you may use. I gave you an example that you're familiar with, but you can think of any coordinates that you like. It's a very general description. Right? See if I can come up with some nice coordinates for this. Alright. Any further questions? People at the back are generally very quiet. No questions asked? Not a good sign at this stage. I'm serious.
Like I can say, can I say that the tensor is a tensor density with weight 1 of 0?
Zero.
Is it weight 0?
Weight 0, yes. I would simply call it a tensor.
Yeah.
A tensor density is something that transforms like a tensor, but with this extra term of Jacobian to some power. That's the exact finish. All right. Okay, good. Now, okay, remember, we're not doing this just, okay. Some of you may think it's fun, some of you may not. So obviously we're not doing it just for fun. We're doing physics. And we're doing all these games because we do need to write physical equations. So I said, this is our original motivation, right? We want to have the ability to write physical equations in a covariant way. And as we know, most of equations, I think even all of equations describing physics can be written in terms of partial derivatives. Take something, take a partial derivative, and then you solve the equation somehow. But the very unfortunate fact is that partial derivatives of tensor is not tensor. It's quite sad. So we need to somehow mitigate this problem. That's what we're going to do now. Covariant derivative. A partial derivative of a tensor is in general not a tensor. That's a major problem if you are to write equations using tensors. So, for example, if I take a vector v mu, which I can write down transformation law, dx mu prime over dx mu v mu. So if I take the partial derivative, dv mu prime over dx lambda prime. D over dx lambda prime of dx mu prime over dx mu v. Let's take first the derivative of the second term. So here I just copied, right? So this is just dx mu prime over dx mu. Now v mu is expressed in terms of the old coordinates. So I can simply take the derivative with respect to the old coordinates. So I just write down dx rho over dx lambda prime d mu over dx rho. take the derivative of the second term. And I have to take the derivative of the first term, of this term here. So this will be b squared x mu prime over dx mu dx rho dx rho over dx lambda prime times v. Right. So if this derivative was a tensorial, then this is what I would expect it to be.
What's going on over there on the right side of the?
Well, nothing. I just took the derivative of dx mu prime.
No, but just in the
dx
right.
mu prime over dx mu with respect to that.
Right, but the right term, there's
So
just
I
a gap.
cannot take that with respect to that. So I have to take it with respect to the old coordinates. So I just write it down as dx mu prime dx mu
Right,
over
this is
dx
plus
rho,
and
and
minus.
then dx rho dx mu prime, and this is just copying the v.
I'm just asking if that's a multiplication or an addition. Or just,
Ah,
just, sorry, it wasn't obvious.
so if this was a tensor, then this is what I would expect the transformation law to be, right? This is transformation of a tensor. But I also have that. Ouch. Because I need the derivatives. Yes, energy conservation, go down to d nu, t mu nu. Euler's equation, conservation of energy and momentum. Remember that? What do I do? This is not going to be a. It's not a tensorial. I cannot write this equation in tensorial way. It's not. It's not going to be true in any space that is not flat. So we need to define a new operator. That transforms as a tensor in general, and in flat space, time reduces to the partial derivative. Right? That is that's what we're going to do in the next half an hour. It's going to be a little bit of algebra, but really it's an algebra, so don't get too excited by it. Algebra is the kind of thing. Just go very, very carefully at home over all the indices, and you make sure that they didn't mess up any index. So, remember we had this thing which you said is not a tensor. What was that?
Tensor.
Yeah. Except from that, that's not really very helpful right now. Yeah, fine connection. So we do the transformation law of the affine connection. It's a little bit annoying, but it's really just algebra, so don't get too nervous by it. Gamma lambda mu nu. So this is d x lambda over d psi alpha, d squared psi alpha over dx mu dx. This was the definition of the affine connection. So now we're going to change coordinates. Coordinate change. Gamma lambda prime u prime is dx by definition dx lambda prime over dx psi alpha, d squared psi alpha over dx u prime dx u prime. Yeah, just copy. So let's try to express that in terms of the old coordinates, right? So we have dx lambda prime over dx rho over dx psi alpha times d over dx mu prime of d psi alpha over dx mu prime. So I'm just going to write this dx sigma over dx mu prime d psi alpha over dx sigma. Right? Just express that. I'm trying to express it in terms of the old coordinates. So dx lambda prime over dx rho over d psi alpha. Now let's open up this here. Again, I'll do first the second term. So I'm not touching the first term at first, so I have a dx sigma over dx mu prime. D over dx mu prime of d psi alpha over dx sigma. I'm going to write, I want to express that in terms of derivative of old coordinates, so it's going to be dx, what did I choose? Tau over dx mu prime d squared psi alpha over dx tau dxc. Now I have this first term, so this would be a d squared x sigma over dx mu prime dx mu prime times d psi alpha over dx. Okay, still with me with the algebra?
Is the first part just what we'd expect if it were tensor?
Nearly.
Well, it's just
I love it as much as you do.
Okay.
Right? But yeah, I mean now.
that's what we saw over there.
So what we have, gamma lambda prime mu prime is this. Is that? This is just gamma rho tau sigma. So we just have dx lambda prime over dx rho, dx sigma over dx mu prime, dx tau over dx mu prime times gamma rho tau sigma. So this is this term. We have the second term. We have dx rho over dx psi alpha. There's dx psi alpha over dx sigma, so this is just a delta rho sigma. So every time I have a sigma, I can simply replace it with a rho. So I have a plus dx lambda prime over dx rho, d squared x rho over dx mu prime dx. Yeah. So if this was a tensor, then the first term is what we would get as the transformation. But we have the second term, which is killing us, as destroying us very nicely. Yeah, no, some parts of this course are a little bit messy. Again, it's just algebra. It's quite straightforward to follow. So I'm gonna write it in a slightly different way, but I think you might be already seeing where I'm heading. So I'm gonna use the following. I'm gonna use dx lambda prime over dx rho over dx mu prime is delta lambda prime mu prime. And then I'm going to take a derivative of that with respect to dx mu prime. This is going to give me 0, so I'm going to have two terms here. So I'm going to write dx lambda prime over dx rho d squared x rho over dx mu prime dx mu prime. Now this is taking the second derivative. instead of having a plus with that derivative, I'm going to write it as being equal to minus b squared x lambda prime. I cannot take the direct derivative here, so I'm just taking this as d x rho dx sigma over dx mu prime, and then dx rho over dx mu prime. Right, I just took the derivative of that. And I'm going to plug that in here. Right? This is this one, and exactly what is written here. So I'm going to write it down as gamma lambda prime mu prime is dx lambda prime over dx rho dx sigma over dx mu prime dx tau over dx mu prime gamma rho tau sigma minus dx sigma over dx mu prime dx rho over dx mu prime d squared x prime over dx rho dx. Okay, it's there. Did you what I did? Just do that. You use that trick to just write that result in a slightly different form. Yeah.
Why can't we just set the problematic term to 0 and see what the constraint?
It's not 0. We want a general transformation.
I thought we just don't want this.
We have a general transformation from x mu to x mu prime.
But without, if we had, this term.
I do have. What do you mean if I didn't have? If I didn't, but I do have. What can I do?
Yeah, I mean, we can get a constraint out of this, and then we can apply it.
No. I want an equation like this equation, which I know is true in flat space. I want to write an equation like that will describe what happens in any curved space. I have a problem. If I take the partial derivative and I'm trying to change coordinates in a general way from x mu to x mu prime, it can be I can stay with the same flat spacetime like I showed you, right? I can write down flat spacetime in curved coordinates, right? And spherical coordinates. I get these terms. It's not something that is not there. It is there. For that equation, for any equation. Here just a general equation for vector. And the same is true for the affine connection. I take the affine connection. This is the way we define the affine connection, right? And I take it and I want to transform that affine connection to a different coordinate system in a general way. And this is what I get. I mean, well, what can I do? This is the math.
So if we do
I don't have any.
So if we do what they say, we just get the private.
We do what you say. That means that we're limiting ourselves to a very subset of spaces. I don't want to do that. I want to do something which is completely general. I didn't say what the space is.
Okay.
Right? Where was the time? We still have a few minutes. So what do I do? I mean, this is not a tensor, right? How this chart feels. Gamma is also not a tensor.
You cancel out the terms.
Yeah, but it smells like we can do something with them. Somehow, miraculously.
Maybe define a new derivative.
That's what I said I want to do. I'm going to define a new operator, a new derivative, which will be covariant, namely transform like a tensor.
It's like what we did in particles course. We had new derivatives on the.
No, it's different. But it's not relevant. Particle is a different course. No, it's a different. It's different. What we're doing now is the goal is to find a new object which will, one, transform like a tensor quantity, and two, in flat space-time will reduce to the partial derivative that we know. So what we want really, what we're doing is a generalization of the concept of derivative into non-flat spaces, into curved spaces. This is what we're really doing here. Should be very clear to all of you, right? And let's do it. This is called the covariant derivative, which is what we're going to do now. So I will. We are running a little bit short of time, so I'm going to erase all that. I want to leave the final result because we're going to use it. So we have that here. I'm not touching it. I'm going to look now at gamma lambda prime mu prime v mu prime. I can do that, right? It's an object. What do we have? Okay, well, just copy from here. Dx lambda prime over dx rho. Dx sigma over dx mu prime, dx tau over dx mu prime, gamma rho tau sigma, basically just copy that, right? Minus dx sigma over dx mu prime, dx rho over dx mu prime, times d squared x lambda prime over dx rho dx sigma. So this is the lambda, and the v, this is just d v mu prime over dx, call it kappa v kappa. It's transformation law for this format. So we have v mu prime, this is cancelling with that term, right? That term and that term. So this is a delta kappa sigma. So every time I have a kappa, I can simply write this as sigma, and I end up with a dx lambda prime over dx rho, dx tau over dx mu prime, gamma rho tau sigma, v sigma. So that's what I get from that term. And from here I get, again, delta kappa rho. So every time I have a kappa, I can simply put the rho inside. So minus dx sigma over dx mu prime, d squared x lambda prime over dx rho dx sigma v rho. Okay. Now I just want to slightly switch things here. I have plenty of dummy indices. I have some indices that I want to change their names. Change the name. So I want to switch the lambda prime and mu prime. I'll write it as mu prime and this is lambda prime. This is going to be a mu prime. This is going to be a lambda prime. And here too, this is going to be a lambda prime and this is going to be a mu prime. That's because I want to switch the names. And then I have these dummy indices. So rho here I want to write it down as a mu. And the sigma I want to write as a rho. So I have a gamma, mu prime, lambda prime, mu prime. The mu prime is, here I have a dx mu prime over dx.
dx mu, no?
Dx
Mu.
Yeah, hold on. I'll do something else. Mu and mu.
you replace rho with mu, then it should be a mu.
Then it should be a mu. Yeah, that's right. Okay, mu, and then this should be dx. And tau I want to change to a rho, right? So,
And change sigma to rho.
oh, what did I do? Oh. Let's see. So before I switch the rho to a mu. Let's see. If I do just like that. Then rho to a mu. Oh yeah, that's fine. And tau to a rho. So rho to a mu.
You said you would switch
Fine.
sigma to
No,
rho.
and tau I want to change to a rho.
You change sigma to
So
rho.
if I say sigma to a rho, I cannot do that. Yeah, so I'm not going to change sigma to a rho. I'm going to change tau to a rho. This is going to change to a rho. This is going to change to a rho. So I have dx mu prime over dx mu, dx rho to dx lambda prime, and then gamma mu rho sigma v sigma. That's okay. And here I want to change rho to a mu, rho to a mu, or maybe a mistake, and sigma to a rho. That is, where is the sigma? And this is sigma to a mu. This is sigma to a rho. These are dummy indices that you have to be careful with the indices, but these are dummies, so I don't care. So I have a minus dx rho over dx lambda prime, d squared x mu prime over dx mu dx rho v mu. Okay, good. That's what I wanted to get. Okay, you all with me? Managed to confuse a little bit myself with all these indices, so I just have to go through carefully. So, but we are nearly there. Because now, I have that function here. Now I can simply add these two equations. So dv mu prime over dx lambda prime plus gamma mu prime lambda prime mu prime v mu prime because the reason why I did that, because this second term here this term here is exactly this term here.
Including the v. No? Including the v.
Including, I thought this is yeah, of course. This down is a plus, and this down is a minus, so it exactly cancel themselves out. So what we have is dx mu prime over dx mu, which we also have here, right? Dx mu prime over dx mu. Dx rho over dx lambda prime. Times dv mu over dx rho plus gamma mu rho sigma v sigma. Which is bingo.
Just from the tensor.
This is the transformation law of a tensor. Which rank?
It would be 1, 1.
1, 1. Okay. So this leads us to define what we call covariant derivative and it's noted by nabla mu, so nabla lambda v mu And the way I will write it is with a semicolon, v mu semicolon lambda. Remember, I wrote the column to denote the partial derivative in flat spacetime. So in curved spaces, it's going to be a semicolon. Right? And it's defined exactly that. dv mu over dx lambda plus gamma mu lambda sigma v sigma. This is exactly what we wanted. Remember, I told you that they find connection, and this is a tensor. This quantity, v mu lambda, is a 1-1 tensor. Is a 1-1 tensor because v u prime lambda prime is dx mu prime over dx mu dx rho over dx lambda prime v mu rho. So we did some algebra, which admittedly is not the nicest thing I did in my life. But we reached what we wanted. Now you can also understand the meaning of this term of fine connection. We'll get deeper into that next week, right? Because it connects different locations, and specifically here we showed this enables us to generalize the concept of partial derivative into a covariant derivative, which means derivative over non-flat spaces. Right? I think this is a good place to stop for today, unless you have any further questions. Maybe I should ask you. Any questions? So go carefully over the math at home. Right? I mean, it's not it's just algebra, and I try to do it very clearly so you see what I'm doing here. Nothing fancy about the algebra, the conceptual. We got the very important reason, because this is something which we can use to solve physical equations in curved space. All right? Okay, so have a nice weekend. I will post a new problem set just to make you feel ready to work. And I'll see you on Sunday morning, right? 10 a.m. See you here.